last 30 years, we've gone through several computing platform revolutions that have brought computers to more people. I think we can all remember Windows and the PC entering our house in the early 90s. We can all remember Netscape and Yahoo bringing us the internet. And then, of course, we can remember the smartphones and the introduction of the iPhone in the mid-2000s, as well as AWS and cloud, so we have mobile cloud. And that brings us to 10 years later, we're now experiencing a new revolution, and that is the AI revolution. So I want to talk to you a little bit about what caused this new modern AI revolution. And deep learning really caused this new modern revolution. Deep learning is a technique that is, these researchers at University of Toronto, many of you know, under Jeff Hinchin's advisory, Ilya and both Alex Kurchevsky, they worked on a problem. It's called ImageNet. We procured a large data set called ImageNet, millions of images with thousands of classes, and they attacked the problem with a brand new type of software. And that software was able to outperform the state-of-the-art by 10%. And before that, the hand-featured computer vision techniques, the state-of-the-art techniques, were hovering around the 70 to 74%, making about incremental progress about 1% per year. And all of a sudden, this neural network technique, this software that Alex had developed, had brought us up by 10% just a year. And it kind of completely shocked the computer vision ecosystem, I would say. And he was able to do that by designing it for new hardware. And that hardware was GPUs, and that's why I'm here talking to you today. That's what NVIDIA does, in case some of you don't know, which I know some of you don't, because I've been speaking with you the last 24 hours. So he designed this software to work on this new type of computing architecture. And it's a parallel processor. It's a different architecture than your typical CPUs. And what the difference was, he was able to train a model in just a few days. And do that single iteration in just a few days, and then do many, many iterations where he was able to just blow the accuracy out of the water from anything previously seen. And that's what's brought us here today into this modern AI. Deep learning since then has achieved superhuman results. So in 2012, after Alex had made this incredible achievement, researchers at NVIDIA, as well as Andrew Ng at Stanford and Adam Coates, they said, well, we know that the model complexity, we know if we can add more layers, we can actually make this thing more accurate. But then computation becomes even more of a barrier. So how can we distribute this problem across many computers? And so they wrote this paper about how they could distribute the problem across many commercial off-the-shelf type of computing systems, which included GPUs. And since then, folks at Google and Microsoft have really commercialized that. They've continued to work on the ImageNet problem, and I say the ImageNet problem is largely solved now. It's kind of in engineering mode. We're at the last couple percent. They broke superhuman barriers in 2015. And even this year, 2016, Microsoft broke another barrier in surpassing human in speech recognition. They're going from convolutional neural networks for images into recurrent neural networks for things like speech. And they're able now to get into word error recognition of 6.3%. So this is really kind of blowing it up, right? The adoption is really, really off the charts. I think hopefully a lot of you sat in on Rob's talk yesterday at Google, and neural networks is a huge portion of the work that they're doing in artificial intelligence at Google. And this chart on the left is Jeff Dean's talk this year, and he talked about over 2,000 applications at Google are now incorporating deep learning. There's another important aspect to when you're thinking about computing platforms. Of course there's hardware, but there's absolutely software. And thank goodness to all the academic labs who created 3 very important packages. There are many more, I can't be all-inclusive here, but Caffe, Torch, and Theano. So Caffe out of Berkeley, Torch out of NYU, and Theano out of Montreal. These are open source academic packages that allowed people to efficiently train neural network models. And then luckily, the GPU is such a great fit for this, and you can go buy it at Fry's or at Best Buy for a couple $100s, that it put this technology in the hands of every researcher. And so you can see now there's an evolution that has taken place in just the last year. Google and TensorFlow, they've been talking a lot about it. Microsoft has created CNTK, very, very good at voice. Amazon has created Destiny, very good at recommendation engines. These are all open source framework packages that you all can get, and you can add, you can start applying it to your data and building your own neural network models. And it's also a global phenomenon here. So there's packages that are coming out of Japan. So Chainer and MXNet are very time series oriented packages because Japan has a lot of IoT and robotics. Baidu just released their Paddle framework. So we talked about it's not just the silicon, it's all the tool chain that's set up on top of it. And you can see how important that is to innovation, as Facebook talked about FB Learner. So there's lots of tools that are coming out here. This is a real opportunity for us to look at how we can make those tools easier and easier to use. And NVIDIA is also investing in that. And just our own experience, the number of organizations that we're interacting with using deep learning for different problem sets has just kind of exploded. 35 times in just 2 years, and as I mentioned, we stood up a startup virtual accelerator program called Inception, and in just 3 months we had over 600 applicants. So, and they're coming from all fields. So it's incredibly exciting times. So if we think about artificial intelligence, it's certainly the ultimate computing challenge, and I want to talk to you a little bit about that. One more reference from Jeff Dean here where he says, you know, the results are going to get better with 3 factors: more data, better models, and lots of compute. And so you can see that with these 2 examples that follow. For ImageNet, as I said, Microsoft competed in ImageNet in 2015. They built a new model called ResNet. AlexNet was Alex Kruszewski's model, and if you can see the difference in the 2, one was 8 layers and it took about 1.5 gigaflops of computation. The next one that appeared 3 years later was 152 layers and it took 22 gigaflops of computation. That is a 16 times complexity in the model for computational complexity, and that's for images. And then speech. If you just look at what Baidu's done with their deep speech model, which is incredibly powerful, and what they've been able to achieve. Deep speech won just 1 year ago. It was, you know, we talked about data being a characteristic. They use about 7,000 hours of training data, and their new model in Deep Speech 2 is 12,000 hours of training time. And so that introduces about 10 times the complexity in computation. And so so 2 things we've solved here now, which are really interesting to think about for artificial intelligence, is sight and sound. So this is pretty phenomenal results in quite a short amount of time. But the thing we all should internalize is when you have a new computing revolution, there is a new computing model. I want to talk to you today about what that new computing model is. So when we think about deep learning, we think about how is software going to be created differently? And where is it going to be deployed? It's all going to change as a result of deep learning. If you think about what deep learning does, it's software writing software, right? If you think about where is the computing industry going to go to support this, server design is going to have to fundamentally change. Data center design will have to fundamentally change. Embedded device design will have to fundamentally change. And so I think if we think about training, where a neural network model, it's billions of trillions of operations, and we want to do it as many times as we can. You know, FBLearn, they always says they want to just keep iterating. We need to make sure we have a compute architecture to support that, and luckily GPUs have been a fantastic solution to that problem. So I want to always love to give real-world examples of how the breadth of deep learning, maybe some you haven't discovered, maybe some that you've heard of before. But if you think about satellite imagery in NASA, right, it's very noisy data. It's huge data. It's a difficult thing for a human to work with. It's a difficult thing even for a computer vision expert to try to make sense of. But applying deep learning, they're able to look for things like vegetation, crop health, landscape changes to really understand what is our carbon impact. That's been amazing work. More mainstream, Pinterest is now using deep learning to do their visual e-commerce and bringing brand new features, bring small business owners new leads and new sales. wonderful features. And this one I really love is the Lettuce Bot. So Lettuce Bot out of Blue River is an agricultural company, and they are able to, they train a neural network, and they have tractors that run across the crops, and they can identify on the fly whether that is a weed or just a piece of lettuce coming up. And they will only shoot the weed with the pesticide. So they're claiming they're saving about 90% of pesticides, and I'm just happy so I can feed my daughters more organic food. And I think we're all super, super delighted about what are the possibilities in healthcare. I started my career in healthcare, so I'm extremely excited about what deep learning is going to do in healthcare. Recently this year in Nature, Mount Sinai published how they were using neural networks with electronic health records. And like you, I like to see other instances of deep learning, not just for images. Electronic health records are such a powerful tool, and they're so locked up right now. The data is so locked up within the walls of the hospital that I can't wait for this to be a tool that brings more information to our clinicians, more information to ourselves as patients. And so what they were able to do is look at 700,000 patient records, and they wanted to see if they could outperform some of their existing hand-featured, hand-engineered predictors for disease. And they've done quite well on diseases such as cancer, diabetes, and even schizophrenia. So the promise there is fantastic. The U.S. Naval Medical Center, they have constraints that they live in, right? They need to be very cost-sensitive. They need to be a very efficient medical center. And they thought, well, pathology is a difficult thing for humans as well, as many of you know. It's to try to find the anomalies in the data sets of pathology are difficult. And so computers are quite good at pattern recognition. And so they put together a model and now deployed it into their workflow to be able to increase the efficiency of the pathology and perform better all around operationally. And then at Mass General Hospital, they use deep learning to assess bone age assessment. So for children looking for different type of growth diseases. And I think what's incredibly impactful is like, okay, well, just for a single patient, it's great to have this augmented, but then you think about how this goes into other areas of the healthcare system. We've heard a lot from the pharma industry, and you could say an algorithm like this could be implemented into clinical trials. So unfortunately, children who have to undergo chemotherapy, they need to be monitored for bone age assessment to make sure that the chemotherapy isn't hurting their growth and creating disorders there. So really, really powerful outcomes of deep learning. And this is where deep learning training and being able to put your data to use is having just fantastic impact. Now I want to go to thinking about when you want to run your deep learning model, you also have to think about what is the computing platform. Deep learning, running the deep learning network is a very parallel problem. And if you want to do it at scale, as many of the applications do, you have to rethink your data center entirely. These workloads of doing, billions of transactions a day, uploading millions of images, of videos, of voice, and having to process them in parallel, you have to rethink your data center so that it's real-time response, so the experience is good, and also that your data center throughput is great. And so one of my favorite applications, I just went to Beijing and I took a short little video of folks playing this hacky sack game. That was fascinating. But Prisma, I'm kind of addicted to it. Prisma and Artisto can add these Van Gogh or these true artistic styles to your own photos. And as soon as I became a user, I was hitting that thing hundreds of times a day, and they were putting 2 million new users a day onto their service. And so this is the kind of thing that they have to plan for. And if you've ever used Prisma, I love you guys, you'll see that sometimes it will come back too many people on the server and they can't process. And so they have to invest in new infrastructure, and that's just a case in point when you want to think about planning for deep learning at scale and in deployment. And so consumers love deep learning, I'm one, but it's also a global phenomenon, right? So you can see in every single major region that there are huge services coming up, consumer applications, and it's really a race. I'm excited about it, and the race is kind of, what I think is wonderful is it's causing this amazing outcome of startup companies. And we've all seen the statistics of the investment and the number of startup companies in this space. And I think there's lots of opportunity to disrupt existing industries and not only create ones that we've been talking about mostly. One you could look at is Deep Instinct, where they're doing using deep learning to do real-time cybersecurity. We also have Deep Genomics, who's looking at DNA mutations. We have Drive AI, who are creating new computing platforms using neural networks for self-driving cars. And as I just mentioned, Prisma for new digital art. We want to also consider what is the impact of this in devices. Deep learning is certainly going to supercharge an area of intelligent IoT. We don't just want dumb IoT, we want smart IoT. So we want to think about how could we put a neural network inside devices? What end devices need a neural network? And what kind of neural network do we need? And certainly you can imagine devices like self-driving cars are one of the most demanding. And so we talk about it a lot because if you go after the most demanding, a lot of the other devices stand to benefit from the technology that was already created. And so for self-driving cars, you have to not only perceive what's in front of you, you have to map and localize so you know where in the world you are, and that will help you plan and then ultimately make a decision. And if we want devices to be intelligent, they will have to have neural networks and models inside the device that allow them to do real-time decision-making, planning, and reacting to their environment. And it's billions of intelligent devices, right? They need to recognize, they need to reason and problem solve. And so GPUs are also finding their way into devices. About 24 hours ago, our CEO delivered a keynote in Europe, and we announced Xavier, which is our latest system-on-a-chip platform. Xavier is architected with our next generation GPU called Volta. It has 8 CPU cores inside, and it even has a special computer vision accelerator inside. And it can do 20 trillion operations per second and 20 watts. So the amount of performance we can pack in a small package is pretty amazing, and it is built for transportation, but you could imagine there will be others for smaller form factor intelligent devices. And so billions of intelligent devices, I get excited about this too. I don't know if any of you have smart cameras at home, but they're just missing so many great features you know are not that far away. But imagine a camera that can see and tell you who's at your front door before you have to open it. Imagine the speaker that you know is going to be coming soon that you talk to so much more naturally. It knows what you want to say, what you want to do, what your next move is. Or all of these autonomous transportation, either if it's a drone flying autonomously into somewhere that is unsafe for humans, or if it's this delivery robot that can bring me groceries, which would be fantastic since I have 2 little ones at home. I want to now talk about, there is an impact that these intelligent devices and all that we talk about today has on the broader enterprise. And so I like to think, while these are wonderful consumer-based applications, I also work for a $7 billion company, and there's a lot of things that we would like to know about our customers, what they're doing, the market. When we launch a product, what are the impressions? We want to leverage all of the big data we have as an enterprise as well. And so I say, what about analytics? What does this all do to analytics? And we now can say, we've been trying for the last several years, 5 to 10 years, to really figure out this digital age. Ever since social came into our being, we're trying to figure out how do we harness that social data to make better business decisions, to understand our markets better, to fine-tune our messages. And now we have an added layer that is upon us, which is these intelligent devices, these sensors that are living out there that can give us even more information about the world. So we've got to really prepare ourselves and think about what is that going to look like. And so right now, today, I kind of give the analogy, I feel as if it's as if computer vision was 5 years ago. Today, an analyst, a subject matter expert, an expert system, is asking questions of the data. Right? They have to understand what are the right questions to ask. Then they ask it. We have the compute core technologies to support it. And we just recently got into building tools that help us visualize it. And that's not so long ago. It's only 2 or 3 years ago that Tableau IPO'd, right? So we have to think about what's going to happen here. And I think if we all start to put our sensors on, you're going to start seeing lots of startup companies. You're going to start to see some of the incumbents paying attention to this. And I'd like to really fantasize about what deep learning is going to do for this as well. So one of the startup companies that we work with, MapD, I could look at this visual all day. MapD has 3 amazing features. They have accelerated query databases, they have intelligent analytics, and they have immersive visualization. And so I'm not talking about deep learning yet, but I am talking about how they're using GPU technology to create this. They're doing dozens and dozens of queries in seconds, and they're in real time visualizing it in a very immersive way. This is a very graphics-oriented problem, a very parallel computing problem, and they've taken advantage of it to provide some incredible insights in a very, very fast manner to let you react to it in real time. And they can ingest these kind of streams that are happening in social networks with connected devices in real time. And then finally, you could imagine now, what will deep learning do on top of that? And so all of the companies who are in this technology stack are now looking at the implications of deep learning, and they're trying to figure out how do they incorporate it. And our hope is that they will bring it into their enterprise software suites so that you can experience as business leaders and as decision makers within your own corporation. So I think I'll end here, where deep learning is absolutely a wonderful revolution. I'm incredibly excited about it, the opportunities. I think we've all benefited from the different AI, consumer applications out there. You've heard from Google, Amazon, Microsoft, IBM. They're all now creating AI as a service, APIs that you can take and deploy into your own product development, and in their cloud services, they're really maturing in that area quite quickly. I think, 2 incredibly important industries that are going to be transformed, where there's a lot of life at stake. Automobiles, there's 1 million car accidents a year we could potentially avoid in the near future. And then we have just unlimited potential in healthcare to unlock the data that's been locked up for so long. And then finally, what is deep learning going to do for our enterprise and analytics? And I predict over the next 12 months, you're going to see a huge evolution in tools and software, and startups and incumbents really get their mindset on how deep learning is going to change their products. So thank you. I'll take questions.
Yep, we have time for a couple questions. It's lunchtime, but of course I welcome you to ask a question or two.
I'll talk to you over lunch too, right? Yeah, sure.
Will you foresee the industrial leaders in GPU space will agree on converge all the instruction sets and the driver standards and make it almost like an open standard?
Are you talking about other GPU manufacturers?
Yeah, everyone in that space work together to come up with like an open standard.
Open standard for deep learning? I'm not sure.
No, for the GPU drivers and instruction sets.
Well, it's difficult. So CUDA is available to everyone for free. All of the math libraries that we have produced, we have worked with all the open source packages to integrate and implement. And that is also open source and for free. So I'm not sure what...
If someone needs to, let's say everyone agree on CUDA, or someone wants to make all the changes, what is the process? Is it still you want your company as a dominant? I'm just asking the question because we know the GPU become a central part of the AI computation platform. My question is what you see in the future? What's the standard will go and how manage it?
Yeah, I guess I'm trying to understand the problem you're trying to overcome. So it's an open platform. It's accessible to everyone. If you want to get access to assembly code, I don't think that's going to happen. But CUDA, the whole point, I think the way that AI has evolved The fact that people don't have to actually write CUDA, and we can put the power of this tool into data scientists, into clinicians' hands, into different domain experts who don't want to actually know how to parallel program, is actually the power of the technology. So whatever happens below it, right now, GPUs are the architecture for neural networks. We don't know what's actually ahead of us in 5 years. And I think we're all going to watch it and see where it goes. But right now, the power of the technology is that it's accessible to everyone. And we're abstracting away, actually, the complexity of the silicon itself on purpose, so more people can access it.
Let's take one more.
Yep, hi.
GPU versus, let's say, Intel 5. Do you think there will be a standardization on how the algorithm will be written, or do you think one versus the other will happen?
I don't know if I can comment very well on that. I mean, I think that I don't know what standardization does in a place where we have to move so fast, other than deal with least common denominators. So at this point in time, we're trying to move this revolution along as fast as possible. Speed is everything. And so whatever architecture can run as fast as we can go, because that is what allows us to innovate, I think we're going to continue on that path.
All right. Thank you, Kimberly. That was great.